For introduction, this study conducted to investigate the relationship between two variables x and y using discrete and continuous least square fitting method. In general, the more days with rainfall, the higher the average relative humidity. Since rainfall increases atmospheric moisture, but the relationship is not always linear because humidity also varies with temperature, wind, and other climatic variables. The next one is objectives. This, uh, this study is conducted to identify the best fitting function to predict future trends in our dataset, to provide interpretation for the prediction, and the last one is to find the error of least square used, which is least square linear, quadratic, and alternative function. As you can see on the table on the left, shows that 20 data points that have one independent variable x, which is the number of days of rainfall, and one dependent variable y, mean relative humidity in percentage. This data is based on Kota Baru City in Kelantan. This data is chosen from an official website, Malaysia government website, which is the Malaysian Meteorological Department, METMalaysia.
Okay, for the question 2, Roman is construct and plot a least square linear function. This table displays the data set collected for our analysis. The first column is the number of index for the data from 1 to 20 data. The second column label xi, which is show the value of the independent variable, which is the number of rainfall. For the third column is yi, contain the corresponding value of the dependent variable, which is mean relative humidity. Okay, for the fourth column, xi square represent the square of each xi value, which is used for calculating the least square line. And the last column is xi yi, show the product of each pair for xi and yi, which is also necessary for our calculation. And at the bottom of the table, we see the total for each column. For the first column is the sum of all xi value is 3288, and the sum of all yi value is 1617.4. The sum of xi square value is 543748, and the last one is the sum of xi yi product is 265883.5. This total will be used to compute the parameter of the least square linear function. Okay, this shows the process of finding the least square linear regression equation using the normal equation method. At the top, we see the general form of the normal equation in metric notation, which allow us to solve for the coefficient of the baseline fit. Okay, the metric on the left contain the number of data point, the sum of the xi value, and the sum of the xi square. The vector in the middle contain the unknown coefficient, which is a0 and a1. On the right is we have the sum of yi value and the product of xi yi. Below, the specific value from our dataset are substituted into the matrices. We have 20 data points, so we substitute all the dataset into the matrices. Okay, for the solving this system given us For A0 is 81.04624, and for the A1 is negative 0.00533. Finally, the result least square regression equation is shown as function fx equal to A0 plus A1x. Okay, we got this equation represent the best fit line for our data, where 81.04624 is the y-intercept and negative 0.00533 is the slope. Okay, this is the graph that generated by Microsoft Excel for the linear graph. Okay, the function is we got negative 0.00533x plus 81.04624.
For the next one is plotting the least square quadratic function of an appropriate degree. Here we choose the degree equal to 2 and the equation A0 plus A1x plus A2x squared. So here we have the 3 by 3 matrix A0, A1 and A2. So 3 by 3 in 3 by 3 matrix we have n sum of x square, sum of x to the power of 3, sum of x to the power of 4. So we just calculate this value from the table and substitute in the matrix given. So after we solve the matrix, we get the value of A0, A1 and A2. This value we will substitute in the function of fx, and then we got the final equation, which is negative 0.0006 x squared plus 0.18941 x and plus 66.01273. This is the quadratic graph that was generated in the Microsoft Excel. So we can see the quadratic line in the graph is equal to the function that we calculated earlier, which is negative 0.006 x squared plus 0.18941 x plus 66 0.01273.
Okay, for the third Roman is a plot of alternative function according to the assigned function. Okay, first we need to identify the expected function, which is 1 over y equal to a plus b over x. To transform the data is new y equal to 1 over y, new x equal to 1 over x. Okay, for a0 we equal to a, and for the a1 equal to b. So we have a 2 by 2 matrix. Okay, on the left we have n for the data, and xi and xi square. For the middle vectors is a0 and a1. For the right vector is yi and the product of xi yi. After substitute the data into matrices, we solve the matrix and we got for value of a0 and a1. Okay, for a0 we got 0.01248554614, and for the a1 equal to negative 0.01918237662. For the final answer, we got fx equal to negative 0.01918x plus 0.01249. Okay, as you guys can see, this is a alternative function graph that have generated by using Microsoft Excel. This function of the graph is fx equal to negative 0.01918x is the slope, and the y-intercept is 0.01249.
On this slide, we analyze the yearly relative humidity data using two regression models, linear and quadratic. This corresponds to part 1 and 2 in the assignment. Starting with linear on the left, we calculate the line of best fit using this square method. For each data point, we compare the actual humidity value with the predicted value from the linear model. The error column shows the difference between the actual and predicted values, and also the E-squared column represents the square of the error of SSE calculation. SSE here means the sum of the error. At the bottom we sum the square errors to get a total SSE approximately 27.71. Next, on the right, we extend it a little bit to search for x cubed, x to the power of 4. This linear model, we compute the predicted values, errors and their squares. Then the SSE for the quadratic model is approximately 27.56, which is slightly lower than the linear one. This tells us that the quadratic model provides a slightly better fit to the data based on the SSE analysis. But we will go on to the next slides. Okay, now we're moving on to part 3. This table shows the analysis using alternative model of transcendental function, which was linearized for easier regression. This method involves transforming the data using the reciprocal of both x and y, which is shown in the question 2, 3 Roman. Okay. Here is we calculate the new x and the new y using our alternative function, which is for the new x it is 1 over x, and for y is 1 over y. So we create a new column for them so that can calculate the value. And then for the approximation of y shows the predicted value based on this model. Then the next two columns display the error and the error squared, which is represent how far of the predicted value are from the actual ones. And then at the bottom of this sum of square errors shown, there's 6.508 times 10 to the power of negative 7, which is significantly smaller than the other SSE from the linear and quadratic models. This low SSE indicate that the transcendental function provide the most accurate fit among all three models tested. It best captures the relationship between the variable of the data set. Okay, for this slide we can see the sum of the error from the three function. Okay, from the linear function, the function is fx equal to 81.74624 minus 0.00533x. The sum of the square error is 27.71. Then for the quadratic function, the fx is negative 0.00060x squared plus 0.18941x plus 66.01273, and the sum of the error is 27.56. 56. And the last function, there is alternative function. The effect is negative 0.0193x plus 0.01249. So for the sum of the square error for alternative function, it is 6.508 times 10 to the power of negative 7. Okay, so from all of three functions, you can see the alternative function show the least value for the data, which is the best fit for a model, and it is also the answer for the 5, which is the best based on the SSC value determine the function that provide the best data. So the answer is the best fit function is alternative function because it has the least square of the error SSE among three functions. So now for the question 3, use the best fitting function identified in question 2 to predict future trend in your dataset. Provide the interpretation for the prediction. Okay, from the previous slide, you can see that the transcendental function is the best fit model for our assignment. So here is the explanation for the question 3. The transcendental function for us is 1 over y equal to a plus b over x. So let's say that we choose x as 165. So we can't use the value of x because our transcendental function indicate that we must transform the x into the 1 over x. So the new x is 0.0060606. Okay, and then we plug it into the function, which is fx equal to negative 0.01918x plus 0.01249. Okay, and after we replace the x into the function, we get the 0.0123737 as the new y, but there is also things that we must do is to change the y into the new y, which is y equal to 1 over y. So after we calculate it, we get new y is 80.81657063. So from this calculate, we predict for the year 2020, the relative humidity percentage is 80.8.
In conclusion, this project successfully modeled Malaysia's yearly mean relative humidity using the three techniques. The transcendental function with transformation provided the most accurate result based on SSE analysis. The model prediction aligned well with actual data, demonstrating the effectiveness of mathematical modeling in environmental forecasting. These findings support future climate study and highlight the value of mathematical tools in solving real-world environment problems. That's all from our group. Thank you for watching.